Thank you. I'm going to speak about the regression discontinuity design, and I'm going against the string. So I'm putting this dedication, which was true at the time, and by now I know who was this colleague of mine. Somebody told me. Just to put things in perspective, that I'm going against the string, I will be very forcefully going against the string, but maybe I'm wrong, I don't know. Okay, but let's start in the old time, the semi-parametric story, which we had one of the models that was considered 40 years ago or so, was a partial linear model. So what do we have there? We have regression, which has two components. One of them is simple linear, the beta 1x, and one is completely non-parametric h of u. And I want to estimate beta. I consider h to be a nuisance parameter. So I want to estimate the effect of x in the presence of u. And the intuition of the analysis of this model and why it is possible to estimate beta actually in the square root n rate, and why would we have an efficient estimation of beta 1, is that if I look only on a small neighborhood of u, then u is essentially fixed, and x is a random variable. I'm looking on the conditional distribution with a mean, which depends on u, g of u. And the regression of y on x is linear with intercept hu, which I don't care about, but the slope is beta 1. So in each neighborhood of u, small neighborhood of u, I have a simple linear model, and beta 1 is common, the slope, and it is common to all of them. The intercept is not interesting. I'm looking only on the slope, and it doesn't depend on u. And therefore, for every u, I can estimate beta 1. So beta 1 is it can be estimated under some conditions. And what I'm going to do is to collect all this small neighborhood. So in the simple case where u is actually real, I didn't restrict myself to real u, but let's look on the real case. I just order the u's by their natural order. The y and the x will be ordered accordingly, and my estimate would be the slope in each small interval, which is simply the difference between yi minus 1 and yi divided by xi plus 1 minus xi. This is very noisy. This is, of course, very noisy estimate, but I'm looking on the expectation, and the expectation is going to work quite nicely. And more generally, I would look on a neighborhood, and I do a weighted least square, but this is technicality. But the main idea can be seen here. By the way, if you have any questions, please ask. If you have any complaints, that's even better. I like to be in a fight. Okay. So let's look on another model. And we have the inference in ultra-high dimensional linear model. So ultra-high is p larger than n. So again, I take beta by regression. Usually, I'll use something like lasso, not necessarily, but something like lasso. Can work. But I consider my beta as vector have two components, beta 1 and beta minus 1. Beta 1 would be finite dimensional, let's say real. Beta 1 would be very high dimensional. And so I have this model, and I want to make inference about beta 1. I want beta 1 to be efficient. And the solution, and there are different variations, but all are the same, basically, because we have single problem and single solution. Find the sparse regression, so y on x minus 1. The regression must be sparse because the dimension is very high. And we can take the residual. So that's y on x1, forget about x minus 1, forgetting about x1. A sparse regression of x1 on x1 minus 1, the variable that I have interest in. And let's look on the residual now. And use your estimate just a regression of R on W. The residual of regressing y on x minus 1 and on the residual of x1 minus x minus 1. And under standard unnecessary condition, like the compatibility, restricted eigenvalue, whatsoever, we can use a lasso or anything similar. So that looks a sort of different problem. And when I first worked on this problem, it looked completely new. When we worked on the semi-parametric model, we considered it as a partial spline model, and this is in line of the original econometrics paper that appears in JASA. And so we return to this model, to this partial linear model, except that I now take H and expand it in some base. So for example, splines. And now I write this model, the partial linear model, I write it like that, which looks very much similar to this. In fact, that's what was done originally. The one thing that I want to say in the very strong sense, this problem and these problems are completely isomorphic. Anything that you can say about that, I can translate to this problem, and vice versa. Rates, bounds, what are the conditions, everything is translatable. These are exactly the same models. Okay. I'm moving now to what we are talking about. The subject of this conference is the regression discontinuity design. Old story, appear in different versions. So it appears in educational psychology would be our standard reference, but it appears in that many other contexts. So the standard example would be students are admitted to a program or get a stipend, depending on a score on a test they take before the program. Those who pass the test are admitted, those who don't pass are not admitted, and I want to estimate the effect of the admission. The problem is that this is, of course, not experiment. The decision to admit or not admit is not exogenous, and therefore I cannot use simple regression, seemingly. So that's a model. W is the 0-1 decision to be admit or not admit. We have some explanatory variables, which would be now nuisance. My interest is solely on alpha. W is 0, 1. If it was an RCT, W was randomized, it was exogenic, it was independent of nu, and everything was simple, except we don't assume that W is independent of nu. Students that are good are more likely to pass the exams, that are better than predicted, so nu is positive, are more likely to pass the exam. W is not independent of nu. As I said, the motivating example is a scholarship or admission. I have this problem, and we'll return to this in the following. So basically, we have treatment, we have background, we have response, and the issue is the responses actually have another component, which is a nu, which I call the individual factor, but the decision to get the treatment depends on Q. So Q depends on nu. Q, the score in the SAT, depends on the same individual, depends on Q, and this affects the treatment. So the conditions for simple regression are not satisfied. That's okay. I could, what I call the pre-modern approach, try to predict nu itself by Q, because they are certainly related, and look on this model. Now, just inject Q to the previous equation, which is not bad. But that's what is not the standard. Okay, what is what I call the modern non-parametric approach? I want to try that the standard argument says like that. Students which are near the threshold, which without loss of generality would be considered to be 0, are similar enough, and to a large extent are a sort of just randomly assigned to be in one side of the 0, of the threshold. So if I want to compare students which are similar with respect to Q, and some of them got the treatment and some of them didn't, I'll restrict my intention to the pink, which I'm not sure that you can see, that it is pink, area to the square. And here I say Q is fixed, it's more or less 0, and I can compare the direct effect of the treatment on this group of students. So there is immediately one price that is paid here. I have large sample, all these dots, but my estimator is going to be based only on very small number of them. So how can I do it? For example, we may use a weighted least square with kernel, which I associate usually with this department. Kernel estimators, so to give weights only to Qs which are of order tau n, and tau n is going to be converging to 0. So the rate is going to be non-parametric. I'm doing non-parametric, and I'll get a non-parametric rate. So the price is very slow rate of convergence. Still, I would claim that it's not really no, sorry. Let me start this. The classical RDD consider only students we don't really care whether they will get it or not. That's the reason they are near the threshold. There are students that are just borderline from our point of view. They may get, from our point of view, they may be admitted, they may not admitted. That's exactly where we put the threshold. So in a way, the threshold, and if it was put in any sense, or in any optimal sense, it will be exactly where the effect of the treatment is zero. That is, we'll try to optimize, if we'll try to optimize the location of the threshold, and in many situations that's what we do, we'll put it where the derivative is zero, which is exactly where I don't care what happens. That's the way we maximize. So the classical RDD approach, not only it's slow, it is slow estimator of uninteresting value. In fact, even the students near the threshold are not all the same. Some are relatively good to what could be hoped, and some are relatively worse than what could be hoped given what we know about them, what we could predict. And so considering them to be all the same, they are just randomly assigned from two sides of the threshold, is a sort of misleading. Okay, so now I'm going to what, to what we do. Okay, the main point that in which we deviate from the crowd is the last line. We have the standard regression that we write for y. But in the same way that I could predict y by x, I can typically predict q by some covariate z. Now, x and z here, in many cases, would be just the same. So I don't say anything about how x and z are related. Sometimes they will be actually the same. Demographic, age, all the demographic variables, all your preparation to the program, whatever the background, all of them would be put both here and here. So x and z are the same. The only, my point of view is if I can explain why your grade post-admission, I can explain q, which is your score pre-admission. And now I have this dual regression equations. And the main assumption is that eta and nu may depend on each other. Probably they depend on each other, but they are independent, or at least with mean zero, given the covariance. The joint distribution of eta and nu is arbitrary. What I cannot explain by x here, I cannot explain by, probably is related to what I cannot explain by z here. So I have the same graph as before, but I take into account the relationship between q and the explanatory variables. So in this graph, x and z are basically the same, the background information. So, what does this give us? Standard DD is based on comparing the very few students who are near the threshold. So basically, I compare students, some of them are slightly above, some of them are slightly below, but being slightly above, slightly below, I have only very few students. We compare against students, that's what we can do, that got, but I want to compare students who got to students who didn't get a scholarship. But now I compare students who did the same relative to what was expected from them. So basically, students with similar value of eta here. And now most students can be compared. So for most students who weren't admitted to the program, there is a student who performed similarly to them, but was admitted because its background in variables were in his favor. So he was expected because the gamma z pushed him up, relative to what he can do by himself. So if I look on the data that I showed before, there is a threshold here, and there is effect of being above the threshold. The threshold is in 0, but it's hard to see. So now let's look on the same graph to a simulation, so I can look on it. And now I compare y, I write y as function of eta. And now I have the two clouds, the admitted and non-admitted, those who were not admitted to those who were admitted. And these are exactly the same points as before. So these points are just another view, sliced differently, but the same view as before. And as you see, now it's very simple to compare, for example, each one of these black lines is a pair of students who could be compared because they have the same level value. One of them is blue and one of them is red. So the only thing that the standard approach can measure is the effect of the program, which is alpha, near q equals 0, which in most of the discussion I will consider fixed, but it's not really fixed, it's approximately fixed. And some of the discussion, it will be completely non-fixed. But basically, I can measure it only around q equals 0 in the standard approach. It is not efficient, that nobody is going to argue. I argue that it's actually even not interesting, because these are the students I don't care about. Okay, so what we do is a partial linear model story. For every value of eta, we regress y on x, find the residual. Here, x and z are the same. I regress the indicator on x and find the residual v. We find alpha eta, the regression coefficient on R on V, on the regression, the standard partial linear model, if you wish, which basically measure how much students who got eta above their test prediction benefited on the average from getting the scholarship. Under, as I said, the strict model, alpha of eta is fixed. Otherwise, I find eventually I can weight all conditional regression like that are done for every value of eta. More generally, I do weighting of them because alpha depends on eta. And since I want to be aggressive, I say that it's interesting, robust, and efficient. And just great. Sorry. Okay. So what is the basic mathematics? I write B eta to be the conditional expectation of nu given eta. So I can write nu as B eta plus epsilon. And this is rewriting of the same equation. If gamma was known, since I measure Q, I would know eta. And if I know eta, this is a partial linear model as we started. So I have a simple partial linear model in this, under this assumption, and I can proceed as we started. Okay. One remark, I must assume that gamma is different from zero. So there is a real proper regression here. If gamma is zero, all my argument is going to fall apart. So that's a necessary condition. If gamma is equal to zero, Q equal eta, here I have Q here. Therefore, this is function of eta, this is function of eta, and alpha looks like unidentifiable because I have to break the function of eta to two parts, which are, one of them is attributed to y and one is not. The reason it is possible at all is because I assume that this function is continuous and I assume that this function is not continuous. Therefore, the only thing that I can estimate is a discontinuity of a non-parametric function. That basically, if I assume that gamma equals zero, and that's what the econometricians, the bad guys in this story, are doing. But I do assume that gamma is different from zero, and therefore this argument is going to fall apart, and I can't proceed with the square root n rate. And let's leave it. I would claim that even under their assumption, they usually don't do the proper rate, but let's keep it. Okay. So what is our contribution? We take care of the ambiguity among the errors in very general form and provide squared consistent estimate of the treatment. To the best of our knowledge, this is the first result in the literature of the RDD that gives a fast parametric rate. Too many referees, unfortunately, try to argue that we are wrong in this statement, and therefore I can say I feel safe because they try to argue that there are, and they couldn't find. And our estimate is basically semi-parametric efficient in the standard sense, and I said it is a sort of extension of the partial linear model, also non-trivial extension. So the main feature is applying a regression model for Q, and the almost entirety of the data can be used, and not just observation in small vicinity of the boundary. Another good thing that basically, unlike the standard approach, our method does not really or heavily depend on the tuning parameters. There would be some tuning parameter, but their value shouldn't be precise in any sense, and the rate and the variance is not going to depend on them. So quite safely, I can say that we don't depend on tuning parameters, unlike the standard approach. Okay. Why the standard PLM doesn't apply is because we don't know eta. We estimate eta. And estimating eta would introduce a lot of technical problems. So the technicality are not trivial, because I don't know eta, and I'm going to plug in eta hat. So we could, and we do, depending on the context, do compare students with, and I'll show you later, compare students with similar values of eta, estimated values of eta. The main line will not go through this way. This would introduce asymptotic bias. If I want efficiency, I cannot go through. I don't know how to go through. Okay. What we do. So the chip is because we do subsampling. That is, we'll divide the sample to 3 subsamples, D1, D2, D3. And we start with, on one of the subsample, estimating gamma of this simple regression function. Now we have the residual, and we plug in to this equation, and eta n is a cubic spline basis, but any to do other things. And now I estimate on D2, after I had eta hat from D1, I can estimate the B and its derivative. Alpha in this stage is, which is a parameter of interest, but in this stage it will be just a nuisance parameter. So now I have initial estimator of B and B prime. And now I get to the bizarre stage. I take the two equations together, write a big regression function that include the y's and q as one equation. I have here the blind basis. The z is modified slightly. Put everything here together, re-estimate gamma, re-estimate the slope, but all of them are sort of a nuisance parameter, and I'm concerned only with alpha of this equation. And this would be our estimate. And then if I want to do efficient, I have to rotate the subsamples twice, put as the major step, the third, each one of the third to be the last, and then we are done. So basically, we effectively estimate the parameter twice, both alpha, beta, and B on D2 and D3, gamma on D1 and D3. This seems to be redundant, but not. We don't know how to avoid it. That's the way we did it. And as I said, the essential estimator is gamma is different from 0. The rest are technical, and which are technical, so I'll just pass them. Is just to claim that we have technicality, we do technical stuff, not only talk. And eventually I get, after all these technical assumptions, I get that the estimator is asymptotically normal, and under if epsilon is actually Gaussian, independent of eta, our estimator is semi-parametrically efficient. Okay, so let's recall what we do. So f here is what used to be b, and x here is what used to be z, but otherwise everything is the same and nothing new. And that what we do, we estimate eta from the second equation and do a sort of modified partial linear model treats on the second. Okay, let's go to some assumptions. Some example. Two examples taken from the RDD literature. We investigated whether putting students on academic probation. So students in that by the end of their freshman year had GPA below a threshold were put on probation on the second year, and this is Canadian data for some large Canadian university, I don't know which one. And it's a selective school, so there is a main campus and two satellite campuses where we're on a lower level. Our variable is the GPA of the student in the first academic term, in the second year, and the treatment is whether a student was put on probation or not. I intentionally skipped one statement in half a sentence. So we have a bunch of covariate here, and the covariate are, as you see, relevant to the second and the first year in the same way. So if I want to use this covariate to predict the GPA in the second year, I would use them to predict the GPA in the first year. And when we applied our method, we got something which is similar to what was appeared in the source. The trick and why, so this is a nice work, except that I just for completeness, I would say, not that interesting, but because this remarks some student left the university, which make all the analysis problematic, its interpretation problematic. So the analysis ignores the fact that students left the university, and therefore maybe the main reason that their GPA went up of the students who were on probation is because the bad apples left the sample. So who knows? I don't think that you can get any conclusion from the data about whether the probation was made. The other example that we consider is the effect of Islamic party affiliation of women's education in Turkey. Again, standard data where 2,700 municipalities were used. The treatment Q was whether the difference in vote share between the largest Islamic party and the largest secular party was our Q. And here we found that there was no real effect of who controlled the municipality, which goes against the standard result in the literature. Okay. Okay. One comment. There was what I considered as a pre-modern approach where RDD, before RDD was introduced, what we do, what we naturally do, what statisticians do all over. If you have something that you don't know, you try to explain it. So if I try to explain it by Q and Q square, I get something like that as my equation, since nu was assumed to depend on Q. So let's try to explain it. That's the natural thing to do. This, of course, by simple algebra, equivalent to writing something like that, except that eta here is not observed and Q here is observed, but otherwise this and this are completely equivalent, can be translated. If I put this model and I put this model, I do the same delta 1, delta 2. As you see, X was changed, by the way, because H now includes the gamma Z. So that's X tilde. And this would be completely perfect if beta eta is quadratic. So that's not a bad approach. I claim that it's actually better than the standard RDD, I believe. Okay, now finally estimating the mean effect to make a point, what we can do when I want to make a point that alpha here is not constant. And I want what to make to point what I mean by compare students. So I'm looking again on the same two equations, estimate gamma, have my residuals from the second line. I partitioned as a group of students or group of subjects to those who are admitted to denied, below and above the threshold. All students are in this one of these two sets, and now I match. So for anyone in the denied group, for anyone in the admitted group, I match him with somebody that is in the denied group and have very close eta. And do vice the opposite. For anyone in the denied group, any J, I find the student in the admitted group, which is closer to him in the sense of the residuals. So for each student in the admitted group, I have this equation. For each student, for each the student who is coupled with him, I have this equation. The only difference, okay, the X are different from here to here, that I don't care. And here we have alpha. So if I look on the difference, I have alpha, I have X, and the B's are approximately canceled. Epsilon has conditional expectation 0, and therefore what I got here is a simple linear equation that I can estimate beta if I want, and alpha if I want. Alpha I want, that's all I talk about. And basically, there is nothing I said here, using any procedure partial linear model, I'm not sure, any procedure for linear model. So now I can estimate the mean contribution. I can estimate different means. For example, sorry, no, I was wrong. I have a linear, partial linear model because of this part. But given the beta, I can look on the average, two averages, and see that, for example, the mean contribution for those who were admitted, what was the contribution of the program to the students who were admitted, what the students who were not admitted and denied, what was the missed opportunity by not admission. Okay, so just on time, let's conclude. The modern RDD the standard RDD is non-parametric, the rate is slow, to estimate only local parametry. It heavily depends on smoothing parameters, and it doesn't have a simple extension to ultra high D because of, for example, the very small sample. The pre-modern, which is the silver, is parametric. The rate is square root of n. I can estimate global parameters, doesn't have really smoothing parameters, and has easy extension to lasso. And finally, our method is non-parametric, has a square root of n, estimates global parameter, hardly depends on smoothing parameter, and has an easy extension to ultra high dimension. So everything is good, I hope. And thank you.